Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we were talking about the stresses, right. We defined the normal stress, we defined the shear stress, right, and we have seen that if you want to define the state of stress at a particular point, so you need 9 stress components, right, in the 3-dimensional state of stress. Now, basically in most of the mechanics problem whatever we will be dealing in this particular course, that will be taking care of the 2-dimensional state of stress. That means, say suppose for example, if you pull a thin sheet, I mean something like this, let me draw it. So, if I pull a thin sheet, rubber sheet or metal sheet or any kind of sheet, right. So, if I pull a thin sheet, so basically the z direction stress you will be whatever you will be observing. So, there is no variation in that z direction stress. So, z direction stress is not coming to the picture, right. So, the basically whatever stresses you are getting here, so they are the planar stress, that means in xy plane whatever stresses are acting, so that will be coming into the picture. Similarly, if you consider a circular ring, okay. So, this is a circular ring where all round say internal pressure, as you have observed when we discussed about the thin walled pressure vessel, right. So, if you consider a circular ring, okay, and inside the circular ring you have all round say pressure, internal pressure, then this kind of problem will converge or will come to a state where you have only 2-dimensional state of stress. In this case only the xy plane, only along the on the xy plane you have the state of stress. Similarly, on this particular circular case, if you consider the polar coordinate systems, the z direction, okay, so normal to this board, there is no variation in the stress. So, all the stress components are confined in the r theta coordinate system. Okay. So, this kind of problem is known as plane stress problem. Okay. So, the formal definition of the plane stress problem is that the stress is existing in a particular plane. Okay. So, therefore, there are no variations in the stress components . in the z direction. So, z direction is nothing but the normal to the board. Okay. So, there is no variation in the stress component in the z direction. Okay. So, therefore, the state of stress at a given point is given by, so you, if you want to define the state of stress at a point in the 3-dimensional state of stress, then how many stress components you had? In the last lecture we discussed 9 stress components, right, but that 9 stress components will be coming to the 4 stress components in plane stress problem. Okay. What are those? Sigma x, I am not writing the second subscript as I told you in the last lecture, now onward we will not be writing, okay, and tau xy, tau yx and sigma y. So, this is the state of stress in the plane stress problem, okay, when you have 2-dimensional state of stress, that means the stress is acting only in xy plane. Similarly, if you consider the polar coordinate system, so that will be sigma r, that is in the radial direction, sigma r, tau r theta, tau theta r and sigma theta, something like that. Okay. Anyway, so now this kind of problem will be dealt in this particular course frequently, and we need to understand that what is the speciality of this particular type of or particular class of problem. So, now here in this figure, if you come back, whatever we have seen in the last lecture, right. So, this is defining your 3-dimensional state of stress, but when it is coming to the plane stress problem, that will take this form. Okay. So, in the z direction or the on the z plane, basically there is no stress, fine, that means sigma z, tau yz, tau zy, those things are not coming into the picture. Now, only you have the stress on x plane, this is your negative x plane, this is your positive x plane. So, you have the stress components acting on these planes. Similarly, this is your negative y plane, this is your positive y plane, the stress components are acting. Okay. Here what we have considered? We have considered one parallelepiped around the point O, as we have done in the last lecture, right. So, you have got 2 x faces and 2 y faces. Now, at this stage we are supposed to define the direction or the sign convention for the stresses. Okay. At this moment we are going to define the sign convention of the stresses. Now, if you come back to this figure, the normal stress sigma x or sigma x prime, sigma y prime or sigma y, whatever you consider, if the normal stress is acting on a particular plane, if I say this normal stress is positive, okay, the positive normal stress is nothing but the stress, the normal stress which is acting on a positive plane towards the positive coordinate axis. What does it mean? That means this sigma x prime, if you consider, this sigma x prime is defined as the positive normal stress. Why it is positive normal stress? Because this is acting on positive x plane and towards the positive x direction. So, therefore, this is positive normal stress. Similarly, the normal stress will be positive if that is acting on negative plane, okay, and towards the negative coordinate axis. What does it mean? If you see the sigma x is acting negative on negative x plane, right, but towards the negative x direction. So, therefore, this sigma x is again positive. So, if it is reverse, then that will be defined as the negative normal stress. So, please let me repeat once again. So, if the normal stress is acting on positive plane towards positive coordinate axis, then that is positive normal stress, or it is if it is acting on negative plane towards negative coordinate axis, then that also will be positive normal stress. So, that means if you think of, if you come back to this figure, the sigma x, this face is my negative x face, this face is my positive x face. So, on both the this is the positive x face and towards the positive x direction. So, therefore, this sigma x is positive. Similarly, on this negative x face towards the negative x direction, sigma x is acting. So, that is also positive. So, what kind of nature you are getting by this normal stress? That is a tension. So, as per our convention that the tensile normal stress is always positive, because that is in line with the definition of or the sign convention whatever we just talked about. Okay. So, the tensile normal stress will be always positive, because that will satisfy that condition, that is on positive plane positive direction, on negative plane negative direction. Now, what about the sigma y? This plane is your positive y plane, this plane is your negative y plane, for example, right. So, on this positive y plane, sigma y is acting in the negative y direction, right. So, as per our definition, sigma y should be negative. Similarly, if you look at this part, this sigma y is acting on the negative y plane, but in the positive y direction. That means, on positive plane negative direction or negative plane positive direction, that normal stress will be always defined as negative normal stress. Okay? Fine. So, similarly, the shear stresses will be defined like that. If it is acting on positive plane positive direction, then that will be positive, or negative plane negative direction, that will be always positive. But if they are acting on positive plane negative direction or negative plane positive direction, then they are negative. So, this is the sign convention you will be following throughout the course. Okay, I hope you have understood. So, I have spent enough time on the sign convention, because the sign convention people generally do the mistake. Okay. So, I do not expect this kind of mistake will come from you. Okay. So, now after this definition, what we can think of? Now, as I told you that on this negative x plane you have got sigma x tau x y, but on this positive x plane you have got sigma x prime tau x y prime, right. So, you have got the variation, right. Why this variation? Because you are travelling from one point to another point, and that is defined, that variation is defined by the directional derivatives, right. So, if I can write the variation in tau x y or whatever, tau x y or sigma x y, tau x y or sigma x or sigma y or tau y x, whatever you consider. So, the variation in tau x y as we move from point to point along a path in the xy plane is given by the, that comes from the mathematics. So, there is nothing to do with that. So, directional derivative of tau xy with respect to the distance measured along the path. So, that you know from the mathematics, right. So, if you follow this, then basically this sigma x prime is equal to sigma x plus delta sigma x del x delta x, right. So, if you come to this figure once again, so sigma x prime, we are defining this sigma x prime is nothing but sigma x that was there on the negative plane, and then from negative plane to positive plane you are moving. Okay. So, that is given by the directional derivative of delta sigma x del x, that is the directional derivative of sigma x basically, right, with respect to the distance delta x. So, you are travelling by a distance delta x, right. Similar to that, we can write tau xy prime is nothing but tau xy plus delta tau xy del x delta x, and so on. So, other stress components you can define likewise. Okay. So, now if you consider the equilibrium condition, so whether the stress you are calculating or you are analyzing, this parallelepiped and all those, each and every point is under equilibrium in that particular system. Whatever body I have shown you, if I say that body is under equilibrium, so each and every point in that body will be under equilibrium, that is coming from the definition whatever we have discussed when we are talking about the equilibrium condition, right. So, if we exploit the equilibrium condition, then basically what we get, and if I, so we are just considering equilibrium condition, okay, and we are taking the moment equilibrium with respect to point O, okay, or the center of the element. Now, if you come to this, so if the point O is at the center of the element, so we are considering moment equilibrium, okay, with respect to the center of the parallelepiped or the element, okay, and that must be 0. So, that gives me, if you look at this figure, whatever is shown now just now. So, in that figure tau xy prime is acting, del y del z into del x by 2. So, tau xy prime del y del z is nothing but the force, okay. Tau xy prime del y del z is nothing but the force acting on x plane towards acting on positive x plane. So, that is nothing but this, right. So, this stress multiplied by del y, this is del y, this is del z. So, that gives you the force on the x positive x plane along the y direction, right. Okay. So, that force multiplied by delta x by 2 is giving you the moment. Okay. Similarly, the next part tau xy delta y delta z, that is the force which is acting on negative x plane along y direction multiplied by del x by 2 minus, if you look at the figure you will get it, tau yx del x del z into del y by 2 plus, sorry, minus tau y x prime to del x to del z to del y by 2 equal to 0. So, now if we expand tau x y prime in terms of tau x y and tau y x prime in terms of tau y x, right, as we have done by using your directional derivative and the distance, then basically finally you will be getting this thing 2 tau x y minus tau y x plus del tau x y del x delta x minus del tau y x del y delta y equal to 0. Because we are not getting any moment from the normal stress, right. We are not getting any moment from the normal stress, because the normal stress is passing through the center of the element. Well, so now if del x and del y tends to 0, that means we are converging to the point O, then basically these two terms will vanish, and then finally you will be getting tau x y equal to tau y x. This is a very important and useful relation. Tau x y is equal to tau y x, right. That means the cross shear is same. Tau x y is equal to tau y x. Similarly, tau x z should be equal to tau z x, and so on. So, all cross shear components are equal, right. So, that gives you basically instead of 9 components, right, instead of 9 stress components whatever you considered in case of 3D state of stress, right. So, that will be coming down to 6. Okay. So, this is very important relation we have established, that is the cross shear is equal. So, I will stop here today. So, in the next lecture we will be discussing about, or we will be taking, or we will be exploiting other equilibrium condition, that is the fourth equilibrium condition, and then we will see that what equation we can derive from that. So, thank you very much.